So, correction. So we had this discussion of if you have an algebra and you extend that to, well, there's kind of the sigma algebra generated by A. That's like the smallest sigma algebra that contains A, the intersection of all sigma algebras that contain A. Then there's, of course, the power set of the underlying space X. That's just the largest space. And then, well, we know that Lebesgue measure, so there's exterior measure. Here, there's the Caratheodory restriction to Caratheodory measurable sets. And then we wanted to prove is that anything that contains, so if we have this other, so if B is another sigma algebra and B contains the sigma algebra generated by the algebra of A, and nu is a measure on B such that nu restricted to A agrees with the pre-measure on A. We wanted to know then B, well, so there's a measure here. That there's a sigma algebra M of Caratheodory measurable things, and that's where we wanted to know that this is true, right? And we proved this. And the proof went like this. Well, we know that mu star is the infimum over all, well, we can still call it mu star of F, where F, so this is of an arbitrary set E, F is a cover of E, and F comes from countable intersections of things in A. And on A delta, mu star, because nu is a measure, so nu has to agree with mu 0, and mu star agrees with mu 0. So this thing is equal to nu of F. And basically what that, we followed that with, so here's the issue, that implies that nu agrees with mu star on all of B, since mu star is defined on B. And why is that? Well, so the intersection of all of these F's in A delta, F's containing our set E, if E is in B, so if E is in B, then if you look at this intersection, that is E, of course. Well, it's not true. Okay, so this is a missing assumption. And moreover, another missing assumption. So if this was the case, and E had finite volume, then, well, eventually this intersection would have finite volume. Question?
I'm kind of lost. What?
I'm trying to fix our proof. I'm trying to add the extra assumptions that we needed implicitly in our proof that B, in our proof of this theorem.
So which claims on the board are true right now?
So at the moment, it's just a discussion. I haven't made a claim yet. I'm reminding you.
Equal signs, so they say things that are
Well,
actually equal or are not equal.
They are propositions which may be true or false depending on whether the assumptions are formulated properly. Okay? So I'm going to write, in a second, I'm going to write the correct theorem. Okay? But the theorem that I proved for you was incomplete. And it was incomplete because it included two assumptions that were implicit, that were used in the proof but not made explicit in the assumption.
Okay.
We proved that limits of continuous functions are continuous. Like Cauchy.
Yeah.
Okay? We used uniform continuity without explicitly assuming uniform continuity. The analogy.
By
analogy. Okay? So one thing is, nobody said that if E is an element of B, then if you take all the A delta sets that contain E, their intersection will recover E.
That's right.
What if it differs based on measure 0?
or measure, or positive measure, or big measure. We could be missing a lot if A delta is very, very rough, and this sigma algebra is much finer than this sigma algebra. Okay? So this is issue 1. Issue 1 needs to be assumed. This is not true unless assumed. And issue 2, even if we assume this, we're still not done, because to know, so then we used, so this was kind of one step in the proof. Issue 2 was that if nu of E is finite, then there exists an F containing, then in this, there exists an F in A delta with nu of F finite, containing E. Yes. Okay, so these two things need to be true in order to prove that B is a subset of F.
Professor, where is this measure B equals to the mu? I think it's on the A's generated set.
Well, so
if it's
mu star is on the power set.
The upper set, such that we equals to mu star. Or
Yes, this is all that we've assumed.
It's mu star or mu.
Mu 0.
Oh, mu 0.
All we know is that when we restrict, what I was claiming before was that if all you know is that it agrees with mu 0 on A, then there can't be any other measures. But, so that is true as long as you don't take a much, much finer, so let me give you a counterexample, which fails these two. So counterexample, which is a standard one. I should have thought of it as we proved this, or one of you should have objected. Well, one of you did object. So counterexample is, here's our set A. So it's finite unions, so that we're closed under finite unions. Finite unions of, we could even take countable unions, which will include finite unions. Well, the thing generated by just half-open subsets of the real line. And the measure, mu 0, on any such, if it's non-empty, is infinity. If this is not the empty set. In other words, if A and B, if there really is room between A and B. Okay? Then the measure that this generates is the trivial measure. It's infinite if it has a single point, and it's 0 otherwise. So then mu star, which is also mu, is either infinity or 0, 0 on the empty set, infinity otherwise. But there's another measure, nu, that agrees on this kind of much more coarse thing, which is only measuring. So the point is, if you take intersections of these half-open sets, if I have a half-open and I intersect it with another half-open, that's another half-open, and the unions are also half-opens. Okay, so the intersection of this and this is the little guy, and the union is the big guy, and both of them are half-open. Okay, but here's another measure. Nu of E is the counting measure. So the counting measure, if there's an interval, then it has infinitely many points. If it has a single point, then it has infinitely many points. And so it agrees with mu 0 on these sets. But, well, it even satisfies part 1, because you can approach by making smaller and smaller. Once you take the, you can approach finite points from F delta sets. The problem is all of those F delta sets have infinite size, even though the limiting set has finite new measure. Infinite measure versus finite new measure. Does that make sense?
So what is, so like if I take just like a single point and then nu that point is like 1, but then the F delta sets would all have infinite measure, like
Yes.
using half open intervals?
Yes, even though they do shrink.
Right.
So issue 1, so you need both assumption 1 and assumption 2. Okay, so So let's state a proper theorem now, whose proof will be exactly the proof we gave, but now the assumptions that were used in the proof will be explicitly assumed.
Do you have the date that we did this on?
We can Google it. So
Okay, yeah. I think
we've,
right
right?
through my notebook as well.
Yes. It was whatever day it was that we proved this theorem. So theorem, let me state a proper theorem now. Theorem.
Were these assumptions made in the, it was like right at the beginning that you were like, oh, this is measurable if and only if this
Well,
happens and like.
So in the books, all they do is they say let B equals M. So if you have another, the kind of Caratheodory uniqueness that is proved is if nu is another measure on the same M that agrees with mu zero
Then
on
they
A,
do the same.
then it agrees with mu.
Regardless of the extra.
That's right. You don't need these extra assumptions because then really you're measuring the same things. There's no question about
Yeah.
B versus M.
Okay.
And I wanted to go one step further, and you can go one step further,
Just with
and
the-
say there is no other sigma algebra. This is the biggest sigma algebra you could have. But that's subject to these constraints with the counterexample as given here. Okay, so this is if B is equal to M, then you can always prove that nu is equal to mu. And they agree, of course, on mu zero. But now I want to study something even stronger, which is that there's no other sigma algebra. There's no bigger sigma algebra. So let's state that as a theorem. Let mu zero on A be a pre-measure. Mu star be the resulting exterior measure. And mu is mu star restricted to the Caratheodory measurable sets, be the measure from Caratheodory construction. Let nu on some other sigma algebra B satisfy so let's call this 0 because it's the only thing we actually want to be true. Nu restricted to A matches mu 0. For every E in whatever nu is supposed to act on, there exists a sequence of F in, let's say Fn in A delta, such that the intersection of these Fn's recovers E.
That's the new assumption.
So you, sorry?
That's the new assumption.
That's the new assumption. So issue 1, that takes care of issue 1. You can zoom down on the set. So maybe let me give you a counterexample to where this doesn't hold. So another example, which is the one that Naveen suggested, look at A being generated by, the algebra generated by intervals n plus 1. So it's like a counting measure, but you only get to count once in each interval. So finite unions of this. And let nu be just Lebesgue measure. So there's no issue with finiteness, but you get the measure wrong because the measure of 0 to a half, which is measurable in nu, but the exterior measure will measure it as length 1 because it has to cover it by something which is of size 1, whereas the true measure is a half. Okay, so the issue is with not being able to close in on your favorite set in your sigma algebra by sets in the algebra.
And you would want the measure to also agree with it.
That's right. So Lebesgue measure does agree with the counting measure because the counting measure gives each of those intervals length 1.
That's part of the assumption.
That's the assumption here.
Oh, okay.
Wait, the counting measure gives us intervals length size 1?
If you have somebody, if you intersect that counting measure, if you intersect, so the counting measure restricted to these intervals. In other words, if you have a set and you want to know what its measure is, and let's say it's a finite, it's a bounded set, you just see how many of these intervals it intersects,
Okay, I got you.
right? Because that's literally what the exterior measure will. How do you cover it? You can only cover it with
Okay, I see.
by sticking that thing of length 1, which agrees with Lebesgue measure 1. It's just that those sets don't zoom in on your favorite Lebesgue measurable set.
Okay.
So then are these assumptions new assumptions we're making too restrictive?
They're the necessary ones because they're counterexamples to both.
And is this like strictly stronger than the previous theorem, or?
Well, the previous theorem was inaccurate. It had used
Oh.
these assumptions in the proof
Restricted?
No, I
without
mean-
explicitly stating them.
I mean, the one that presented in the books, where you don't have these assumptions, but you assume that m equals
The-
b.
Yes, so those don't have any of these issues because once m is equal to b, there's no issue about 1 or 2.
Right. So are there? I mean, yeah. Oh yeah, yeah, yeah. Okay, yeah.
So 1 or 2 is because I'm more what's the word? Ambitious, thank you. Right? And flew too high. And 2 is that if the new measure of E is finite, then there exists an F in a delta containing E such that the F measure of this is finite.
You say FN or F?
Sorry.
Oh, okay.
So here I want to know that there's a sequence of A delta sets that shrinks down to E. And here I want to know, well, if there is a sequence and it shrinks down to E and the new measure of E is finite, I had better have the F measure, the new measure of F being finite. Because shrinking things, the limits of measures of shrinking things do converge as long as at least one of them is finite.
Well, all we've said is that there is one which is finite,
Yes?
but maybe there's a way to take a shrinking family such that none of the measures eventually become finite.
But that's okay, just take this, throw this one into your set
Intersected.
and intersect it with everybody.
Yeah, so we can find one.
This says
That's
we can
all.
find one that will be finite in measure, and this says, and we can find enough of them that zoom in on E, and you combine these two together, and that's exactly what we used in the proof. Okay, so conclusion, then B is a subset of M, and nu is mu restricted to B. So what the book covers is the case B is equal to M, then we prove this. There's nothing wrong with that proof. To do the more ambitious thing, we proved it using these two assumptions, but these two assumptions are necessary because they're counterexamples to both of them, both of them failing. Okay, any questions? Thank you, Naveen.
I think the book uses the condition of sigma's finite.
Yes, and we want sigma finiteness. Well, that actually takes implicitly, or whatever, takes care of part 2. Yeah, so let's just add sigma finiteness everywhere because it makes a lot of things easier.
So you mean that the sigma finite is equivalent to condition 2?
So certainly sigma finiteness implies condition 2.
Why does sigma finiteness of mu0 imply this?
So you can intersect the F's if nu, let's think about this. So you can make a series of, so if there's a set of A's which have finite measure and expand out to all of X, then, and this holds, so I'm going to go in one direction and the other direction. So, and this holds rather, and this holds, so the measure is finite. Then just take this F and intersect it with larger and larger A's, and
Sorry, what F are we taking?
so take any F that contains E that's in A delta,
Okay.
okay? And if the new measure of this is finite, then take the intersection with the increasing sequence of A balls, and all of those have finite measure, and you can sort of increase them. You have to argue a little bit. You have to argue a bit. Maybe I had to leave it as an exercise, but you should be able to find, because the growth here is in terms of A's, and now you're taking A deltas, and it's just a single intersection extra to get this sequence. See, these are coming down onto E, and the sigma finiteness is growing out to X, and you have to be a little bit careful about how to get those two to work together. If the worst comes to worst, you put a delta sigma, then it's certainly true, because you're taking sums of unions. You're taking unions of intersections.
I just think A could be very not fine, and we need it to contain F in this. So maybe F gets very small towards infinity.
In the interest of what I really want to cover today, which is finish Radon-Nikodym, let's just assume that it's sigma finite. In which case, everything is, I think, okay. Instead of trying to prove that it's if and only if. Okay? This is how we get. I like these discussions. I like the arguing and the wait a second, when are we using this? Let's find all the counterexamples and so on. But I also want to cover material. So let's leave. Should I say this as an exercise? Exercise.
Prove or disprove.
Right. To if and only if sigma finite question mark. Okay? Play with that. That's a good question. Nice open-ended question. Okay. How far did we get last time? We got through the Reisz representation theorem, yes? Okay, we proved, so recall, proved Reisz representation theorem. What does it say? What does it say? Yes, so let H be the Hilbert space. In particular, I'm thinking of L2. And L is
continuous or bounded?
Yeah, continuous equivalently bounded linear functional. And there exists a G in the Hilbert space such that for all F in the Hilbert space, what L does to it is take the inner product with G. And it's even easy to construct. The proof, I hope you appreciate, is very constructive. It seems like a very abstract thing. Some people think the Radon-Nikodym, it's a very abstract thing.
G was unique, right?
Yeah, thank you. And it is unique.
We can say something about the operator norm.
And that easily implies that the operator norm of L is the operator norm of G. Yes. So let's just look at this. Recall the proof very quickly. Recall the proof. Just to solidify the fact that these are constructive. So you set S to be the set of F such that L of F is 0. Right. This is a closed subspace. S perp. Well, if it has nobody, so the dimension is 0 or 1 dimensional. Why is it at most 1 dimensional? So if it's 0 dimensional, then it's the empty space, and S is all of H, and the linear operator just kills everybody. That's an easy case of G equals 0. If you have two elements of S perp, well, you take L of 1, which is not 0, and you subtract it from the L of the other one times the other one. Should I write this out? If H1 and H2 are in S perp, then let's see, L of H2, H1 minus, or better yet, let's do it like this, L of H1 over L of H2, which we know is not 0, times H2. What happens when you apply L to this?
0.
Yes. So any two elements are up to an element of S linearly dependent. Okay? So this condition is a one-dimensional, codimension 1 condition. Okay?
Did we use boundedness anywhere? Or
We use boundedness to know, well, we use the continuity to know that there's a closed space. And closedness is necessary to write H as S direct sum S perp. Okay?
So is there a Hilbert space version of the rank nullity theorem?
There is.
It's just the same theorem, right?
It's the same theorem, yeah.
That's all infinite dimensional. So.
Yeah. You have to sort
To
of,
figure out how to phrase it.
yeah, you have to phrase it the right way. Okay, bless you.
Thanks.
So, so here's the one, okay, so the point is, some of you asked, so then you let, so if there is somebody in here, maybe it's zero dimensional, in which case the whole thing is 0, you let G be, what was it, is like L of H bar times H over norm H squared. And the point is, because this space is one-dimensional, this is invariant under replacing H by a constant multiple, because the same constant appears twice there and there. So this is a unique element. And it satisfies the conditions. Okay? So all you have to do is find a single element of H which has L not equal to 0. And then you're done with the Reisz representation theorem. So that's very constructive, and now we're going to use that to prove the Radon-Nikodym theorem. Okay? Any questions?
What does the bar mean again? Over.
This bar?
Yeah.
This is a complex number.
Oh, okay. So it's conjugate. Okay.
So can you tell me again what if each one, each two belongs to S perp, and then
So I'm trying to argue that that S perp really is at most one-dimensional. So if you have two elements, then one is a constant multiple of the other plus an element of S. So they can't be linearly independent. There can't be an H1 and an H2 which are both orthogonal to everybody in S.
okay.
Okay.
And there we use that they're.
I'm using that
not-
this number is not 0
Right. Yeah. Yeah.
to make that linear combination. Okay, let's state the Radon-Nikodym since we've been in Hilbert space world a little while. Hopefully you'll remember. Actually, this is what I want to kind of keep in mind.
Radon-Nikodym was what we started, right? And then we took the detour.
Several classes ago, yes.
Okay.
Radon-Nikodym theorem. So what's the setup? We have a sigma finite. Well, both measures will be sigma finite. The measurable space, you can't say it's sigma finite until you give a measure. So this is a measurable space. Measurable space. Nu is a sigma finite signed measure. Any sigma finite signed measure. Mu is any sigma finite positive measure. No relation between mu and nu at all. Then there exist unique measures, positive measures, nu A and nu S, such that nu is nu A plus nu S. Nu S has an S because it's singular to mu. Nu A is absolutely A for absolutely continuous with respect to mu. So anything that has measure 0, any set that has mu measure 0 also has nu A measure 0. And there exists a unique element that is extended L1 integral with respect to mu, such that the nu A measure of any measurable set E is obtained by the Lebesgue integral of this F over E with respect to mu. And this F is the Radon-Nikodym derivative. which is written d nu a d mu. Which is just notation. These symbols do not have meaning beyond this, although they behave the way derivatives behave. So let's prove this. We remember the statement? No, okay. We spent enough time in Hilbert space world.
What does it mean again for a sign measure to be sigma finite? Does it mean the absolute value is?
Exactly. Yep, the total variation is sigma finite. So the total variation, remember, the Jordan decomposition theorem says that nu can be decomposed into nu plus minus nu minus, just like functions can be decomposed. Sign measures are just differences of positive measures, one of which is finite on all of x, at least one of which.
So this is it looks similar now that we've seen the Hilbert space stuff. So the other thing, the integral is sort of like inner product E, like you're taking everything with respect to, f, right?
It does look similar, yes, that this is like an inner product with respect to f, that the only way to get another measure is to get an inner product with respect to f. Yes. And in fact, the proof will use Reisz representation theorem very heavily. But you have to somehow, this is an L1, it looks like an L1 theorem, but we're going to use an L2 theorem to get to this L1 theorem. Okay? Any questions so far?
Is that mu a and mu is must bigger than 0 because v is the...
I just mean it's a positive measure, as opposed to a
v
sign
is
measure.
v. It's v, not mu. It's v equals to va plus vs, then it must bigger than 0.
These are both sign measures.
Yes.
These are not, sorry.
Yes, if they're both bigger than 0. And
Yeah,
I'm
yeah,
sorry.
yes.
I'm sorry. These are sign measures. These are sign measures. These are not non-negative. Thank you. These are
Good
sign
point.
measures.
Yeah.
In the Jordan decomposition, there are two positive measures, so that nu is the difference between them. Here, I just want I can't control their sign. These are both sign measures. Okay. Let's do it. Let's do it. Okay. Step one. Let's assume that nu, first of all, is just a positive measure, and that both nu and mu are not just sigma finite, but just plain finite. That's the first approximation. Okay. Let's consider the following operator. What I want to do is take L of a L2 function. So again, let rho be nu plus mu. So this is also a finite measure. Rho of the entire space is also finite. And I'm going to define, I'm going to apply the Radon-Nikodym theorem, so I need an L2 space for psi in L2 of rho. Let L of psi, I'm going to give you a linear operator in this L2 space. Here's what you do. You take the integral of psi d nu. Okay? There's no funny business with the sigma algebras. We're all on the same sigma algebra. We're all friends here. So there's no question about measurability. And that's linear functional. Okay? So this is clearly a linear functional. A linear functional. I need to know that it sends L2 things to a finite number. I assume this was L2. But I'm taking an L1 integral. I don't know that this converges. Okay? So I need to know that L is actually a bounded, is L bounded or continuous?
Is that this finite support.
Yes.
Yeah, exactly.
Yes. Yes. So this is the integral, again, over x of psi times 1 d nu. And if we only had, so an absolute value, so, well, now it's no longer equal once I put absolute values. So what do we know about, well, let's first use the triangle inequality. This is psi d nu. But nu is positive, so I didn't need the absolute values there. And if we only had some inequality that told us, and I wanted to keep the times 1 there, but I've run out of room. So if we only had some inequality that told us what to do with this thing, Cauchy-Schwarz. Okay, Cauchy-Schwarz. Cauchy-Schwarz tells us this is at most the integral over x of psi squared d nu to the 1/2 times the integral of x of 1 d nu to the 1/2.
So in the definitions, we are integrating of phi prime and
Over x,
oh yeah.
over the space x.
Professor, are we integrating with respect to the total variation now on the?
So I assumed that nu is positive, so I didn't need, so the total variation is the same as the measure itself. Because total variation is plus part plus the minus part, there's no minus part. I just put it there in case, in general, you would need to put it there. But in this case, we've assumed it's finite, we've assumed it's positive, and we've assumed it's finite. So it's bounded, right? The L2, so this is just the L2 norm, which we assume is finite. So is L bounded? The norm, the operator norm of L is in fact bounded by,
The measure of x.
yes, the new measure of x to the 1/2.
I have a question about this, right? We define a function to be measurable if and only if the absolute value, the integral of the absolute value is finite, right?
We define it to be integrable if
Yeah.
the integral of the absolute value
So
is
in
finite.
order for this to be like a well-defined expression, don't we have to do this with absolute value of psi inside first?
So I want to know if this thing converges. I want to know if this makes sense. So
Yeah.
the first thing I'll do is I'll take the absolute value inside, exactly as you said.
Oh, right, yeah, this is what we did. Yeah.
And then I want to know if that is finite.
Yeah.
Cauchy-Schwarz tells me I can square
Yeah,
it.
Exactly.
The assumption was that the square integral of this thing is finite.
Mhm.
And the other assumption was that nu of x is finite.
So then that one tells us it's integrable, and the other one tells us that, yeah.
That it's a bounded operator.
Yeah, okay.
Okay? So this is a bounded operator. So we can use the Reisz representation theorem. Okay?
So we said that C was L2 of rho. I guess that's fine because rho is just the sum of nu and nu.
Yep. So this is at worst the,
Yeah.
maybe I could have done it here, that this is at most the sum of, the integral of rho d, the integral of psi d rho, since rho is an upper bound for nu. Okay. Now let's use Reisz. There exists a unique G in L2 of rho, that's our Hilbert space, such that, I don't want to lose what L is, such that L of psi is equal to the inner product of psi with G. What is the inner product? Well, it's the Hilbert space inner product. That's the integral over x of psi g bar d rho. How did we define this linear functional? It was the integral of psi d nu. Of course, over x.
I think the definition is phi prime or I might be wrong.
The definition is right here, the integral of psi
Phi
d nu.
prime, phi prime, not prime.
Oh, that's not a prime, that's a comma from
Oh yeah.
From L2.
Sorry.
Yes, let me put it like that. Or let me put a box around it. This is the key idea. Again, this is von Neumann's idea. Okay? And integrating d rho is, of course, the same as integrating d nu and then adding plus the integral d mu. Okay? Let's stick in, so now let's apply this formula. Apply to psi is the indicator function of some measurable set E. Let's see what this says. This is nu of E. Okay. This is equal to well, let me write that out explicitly. It's the integral of over x of chi e d nu. On this side, we have the integral over x chi e g bar d nu plus the integral chi e g bar d mu. Okay, so the first thing I want to say, let's move this sum. So let's say that if rho of E is finite, that implies that this is finite.
Rho is finite, right?
Rho is itself a finite measure because E and mu are both nu and mu are both finite measure. So if rho is finite, let's look at this. Let's look at this. Is finite but positive. Let's do it like this. Let's make it positive. Then, this number, so again, this is L of this number, nu of E. Nu of E, which is L of the indicator function of E, which is the indicator of chi E d nu. On the other side is the integral over E of g bar d rho. Okay? Now, these are all equal signs, but nu of E is at most rho of E, since rho is pointwise defined to be nu plus mu. This is non-negative.
Why does that last inequality happen?
That's just because rho is nu plus mu,
And they're positive.
and mu is positive.
What about G bar? Where does that go to?
Well, G bar is just, I'm going to understand, I'm going to learn something about G.
Okay.
The first thing I want to learn about G is that actually it's real. And the next thing I want to learn about G is that it has to lie between 0 and 1.
But we're assuming that when we write the inequality, or am I missing something?
Oh no, this inequality is coming from here.
Oh, okay, I got you.
These are all straight equal signs. And then the inequality is, maybe I'll,
Yeah. No, I got that. I thought we were saying that well, it is. Got you.
okay? We're headed towards, this is the first hint that G can't be big, bigger than 1. So, what this means is that 0 is at least the integral of g bar d rho. I assume that rho of E is not 0, so I can divide by rho of E. 1 over any E divided by rho of E. And that's at most 1. And this is true for all E and M, at least the ones with rho of E positive. Let me leave it as a pleasant exercise. It's very similar to other problems you've solved. Exercise. This implies that G is in fact real valued function, not a complex valued function, so the bar you don't need. And moreover, for rho almost every value of x, g lies between 0 and 1. If there was some complex value, then you could, over some region, then you could integrate over it. If the imaginary part had some, okay, I'm doing the exercise for you. You know what to do. You know how to do this.
Can we say AE for both of these things?
Yes.
And which AE is like?
So rho AE.
Okay.
How is G defined again?
G came from the Reisz representation theorem. That's why I wanted.
What is the unique?
Is the unique function coming from the Reisz representation theorem that guarantees.
Okay, so what this is saying is that our unique function has to be very restricted.
It's very restrictive. Yes, in this context. The one that applies to, it's not in general true, it's the one that applies to this linear functional that we wrote down. I mean, it has to. Look at the linear functional that we wrote down. It's to take the inner product with respect to nu of psi, and the inner product in the Hilbert space is to integrate with respect to rho, and rho is bigger. So we're just kind of following the very logical conclusion that the only way that can happen is if you're integrating against a non-negative function, which is no more than 1. And I'm pointing to where you can't see. Okay? So far so good? This makes sense?
Why is chi e dv equals to g bar d rho?
Chi e dv,
Yes.
the Reisz representation theorem, that's just coming straight from here. That's straight from here. So this is the integral of chi e g bar d rho.
Oh yeah.
Okay? And now I want to separate the action of rho
Wow.
on these two spaces. Okay? So, what have we learned? What have we learned? I guess I can take this away and make some room. What have we learned? To summarize, summary, what page is this? There exists a G, which is in 0, 1 almost everywhere, and in L2. The values are in 0, 0, 1. It's in L2 of x with rho, and it's unique, such that L of anything, which was the integral of psi d nu, is equal to the integral of psi g bar, but I don't need a bar anymore, d rho. Question?
G is real almost everywhere, or?
Almost everywhere, yes. So both of these things are true, rho almost everywhere. Because we're integrating here with respect to rho. Okay?
Or we already decided it's real.
We already decided it's
Yeah,
real.
good.
And-
When we write the inequality, sorry to interrupt, but when we write the inequality right there, like with 0 less than or equal to integral, are we like implicitly assuming the imaginary part of the in between is 0 there?
No.
But otherwise the inequality doesn't make any sense?
Well,
I realize that's part of the exercise maybe, but.
that's the whole point of this. Nu of E, nu is a positive measure, so that's not negative. Reisz representation theorem says nu of E is equal to the integral of E of g bar d rho.
Yeah.
So if it's equal,
So-
it doesn't have a measure.
Right. Well, so maybe we could have done it, maybe we could have done the realness all the way up here, because rho is real and non-negative. G bar, if it has any imaginary part on any set E,
Integrate to
then this doesn't,
Okay, got it.
doesn't make sense.
Wait, so is it saying that it goes almost everywhere on the domain X or almost everywhere on the set E?
So the fact that this inequality holds for every measurable E, at least the ones with positive measure,
Implies almost everywhere on X.
implies rho almost everywhere on X, yes. Now here's the really slick part. Let's break this up as d nu plus d mu. And let's move this bit to the other side. So what we have is that the integral of any L2 function psi times 1 minus g d nu is equal to the integral over psi of g d mu. All I did was move this g to the other side. Everything's absolutely convergent. No problem with absolute values. G is less than 1. So this is still non-negative. Now, a couple of things could happen. Well, if G is equal to 1, so if we take the indicator function where G is equal to 1, everywhere here we're going to get 0. Yeah. But if G is less than 1, then these things should feel each other. You see? The two sides have to feel each other unless G is equal to 1. That's the hint about the singularity versus the absolute continuity. If G is equal to 1, then no matter what nu is trying to do, mu will not feel it. So let's do it here. Let A be the set of x in X for which G is strictly less than 1. Now, of course, this uniqueness is only up to representatives, so just fix one representative and do everything with that fixed representative. So, fix G in the row almost everywhere elements of G. In particular, fix it so that this happens pointwise and not almost everywhere, that it's always between 0 and 1. And B is the set of X where G is equal to 1. And we know that exhausts X. So obviously A is disjoint from B, and their disjoint union is X. Once we've chosen a representative so that those things are true pointwise and not almost everywhere. Okay? So let's check it out. I guess I can even do it here. Let nu, so which one is going to be absolutely continuous? So one of these, I'm going to save a little room there. Nu of E be defined to be nu of E intersect A.
That's probably the absolutely continuous.
That's the absolutely
Why
continuous
else would we
one.
write A?
Why? Oh, right. I didn't intend it that way, but it did work out. The point is right here, if G is not equal to 1, then these two sets feel each other. So that's the absolutely continuous part, I claim. And let nu singular be nu A intersect, of E intersect B. Okay, so claim, which is a pretty easy claim nu singular is indeed singular with respect to mu. Proof? How do you prove this? So we already know that what nu S of A is. What does it mean for two things to be mutually singular?
Find the disjoint sets.
There's disjoint sets,
A and B.
so that one takes measure 0 on one, and the other one takes measure 0 on the other.
So it's 0, right?
Nu of A is 0 because it's A intersect B, and A intersect B is nothing. Okay, what about mu of B?
Use the inequality from up above and get to that 0, I think.
Yes. So let's take or let psi be the indicator function of B, then I don't know what to call this, star, then star gives the indicator function of b, 1 minus g, d nu is equal to the integral of g. Yeah, I can't show both at the same time, can I? D mu, but g is exactly 1 on b. B is defined to be the thing where g is exactly 1, so this is just the integral of 1 d mu, which is mu of b. On the other side, g is exactly 1 on b, so we're integrating the function 0. So we do know that nu s is singular with respect to mu. As it must be. Now we have to show that, so is it true that nu is absolutely continuous with respect to nu A? Okay, so claim 2, let's see, how do I do this? We remember what these sets A and B are. I want to go back to, I want to keep star around. Star is the thing that's going to imply everything we want. So claim 2 is that nu A is absolutely continuous with respect to mu. Proof. If mu of E is 0, then let psi be the indicator function of E, and star gives, what does star give? The integral over E of 1 minus g d mu is equal to the integral of E of some function g d mu, but mu gives that set 0, gives that set measure 0. This is strictly positive on E. Sorry, this is no, that's correct. So what am I trying to say? I'm trying to say that the mass of nu A on E, I'm doing 2 steps at once. So I can put here A intersect E, or not, because there's a 1 minus g. So whether I intersect it with E or not gives me the same answer, because 1 minus g is 0 on that set.
Wait, 1 minus g is 0 on A?
1 minus g is 0 on B,
Yeah. Oh.
and so I may as well intersect with A. But this is nothing but this integral over, which is equal to the integral over E of 1 minus g d nu A. Because what d nu A does is just takes everything that nu does and intersects it with A. So if you integrate a strictly positive function on a measure, well, here everything is positive because we assume the original sets nu were positive. So you're integrating a positive measure, a strictly positive function over a set, and the integral is coming out to 0. That can only happen if nu, which implies nu A of E equals 0. In other words, mu equals 0 implies nu A of E equals 0. That's what it means to be absolutely continuous. There was a hand? Somebody? No.
Wait, can you go through that again?
Yes. So suppose we have a set E which has mu measure 0.
Sure.
Okay? So take in star, where's star? We lost star?
I remember it.
Okay, you remember it, you know what it says. So take chi E for psi in star. So what that reads is the integral of over e of 1 minus g d nu is 0.
Yeah.
Now this integral, because I want, if g is equal to 1, then I'm integrating 0. So I may as well restrict to where we're not integrating over on the 0 function.
Yeah, I'm more worried about, not worried, but like, I don't understand why nu of A is equal to.
The definition of nu of A is you do nu except only on A. You just intersect everything with A.
Right.
So if you just look at what the integral is doing, that's the same as integrating 1 minus g over this d nu of A instead of over d nu.
Right.
Does that make sense? And now this is, I guess I want the strictly positive sign here. It's a strictly positive function in the support of nu A. And that integral is coming out to 0.
Right. I didn't, okay. The chain's going that way.
The chain's going all the way that way.
Yes, okay.
Let me put it, chain it around.
Why does star give us equals 0 in the very first one?
Because on the other side, it's the integral over g of d mu.
Integral on the other side, so yes.
Maybe I'll put it explicitly if I can fit it. But mu has e measure 0.
Oh, that's right.
So it doesn't matter what you're integrating.
Yep.
Mu has e measure 0.
Why did we switch to A intersect E then? That must be after that, okay.
Yeah.
Yeah.
Should I write it out again? No, I think we're okay. Does that make sense?
Yeah.
This is the key part of the argument. There's one more key step coming. So we've proved that nu s is indeed singular. We've proved that nu a is indeed absolutely continuous. All we need is to get that Radon-Nikodym derivative. Okay. So, watch this. This is really fun. And I think I can even do it. Is that accurate
Yes.
for once? But a little ahead. All right. Okay, now, last step. So we still need the Radon-Nikodym derivative. So here's what you do. Take psi equals, bless you, the indicator function of your favorite set E times 1 plus g squared up to g to the n for a fixed n. Okay? What does that give? This is really cool. So in star again. So again, star says if you integrate some function, like this function, so that'll come out to e times 1 plus g to the n, and you multiply it by 1 minus g, and you integrate d nu a, because we may as well integrate d nu a on that side, because there's a 1 minus g there.
1 minus g to the n plus.
That'll come out to the same integral, so the integral over e, and then 1 plus g and so on, plus g to the n, times, so that was just the function, times g d mu.
Why can we integrate with respect to nu a now?
Because this integral is always with respect to nu a. It's dead on b, so you just intersect everything with a, capital A.
That's d mu.
This is d mu. I don't know how to make it a better mu. Is that better or worse? Okay? Now, what is this? This is, of course, equal to 1 minus g to the what? N plus 1 or something?
Yep.
Over 1 minus g. The support of this is where g is not equal to 0. In fact, we're multiplying by 1 minus g. So this entire function is bounded, absolutely bounded. And in fact, it's bounded by 1. So I can use the dominated convergence theorem. So dominated convergence theorem tells us we can take the limit. Dominated convergence theorem tells us we can take the limit. So this limit is the integral. So I can take the limit from the outside to the inside on this side. How about on this side? Well, these two things are equal when the limits are on the inside, when the functions are on the inside.
So the limits outside are equal.
So the limits outside are equal. So that tells me that the integral of e over any set e of 1 over 1 minus g, which is the limiting function, times 1 minus g, d nu a, is equal to, what limit do I get here? Well, I have a g and a 1 minus g d mu.
Wait, I missed why we could apply dominated convergence to the right-hand side.
We're not. So we're applying, look on the inside.
Oh, we're just using
the equality.
Identity in the inside.
The identity on the inside tells us this. And then we use the limit on the outside to know that this converges to this.
Yeah.
And here, what have we found? We found this is nothing but nu a of e. What is nu a of e? It's the integral d mu of e of some function. So this is the Radon-Nikodym derivative. So this is what I love about so some people think Radon-Nikodym, Reisz representation, these are very kind of abstract things. There exists some weird function. No, these things you can really compute. Let's remember where this came from. G just came from the Reisz representation theorem. The Reisz representation theorem was an explicit construction. You just compute you find one element that's not zero, whose linear image is not the zero constant number, complex number 0. Out of that, you cook up a g in a very explicit way. There's your g. You stick g divided by 1 minus g, and that's your Radon-Nikodym derivative. So it's very explicit, very constructive proof. Should we review what happened? Because a lot of things happened.
Yes.
Let's review what happened. So let's go back.
Why don't we take psi direct as characteristic E divided by 1 minus G?
One more time?
Why don't we take psi as characteristic E divided by 1 minus G?
In here?
Yeah.
Because we already have a 1 minus g. In star, there's a 1 minus g sitting there.
Yeah, so I'm saying take psi as characteristic E divided by 1 minus G.
Oh, well, in fact, so it's to get it to the other side. In other words, you're saying, why don't we just in this theorem put that? Well, if I take characteristic of 1 minus g, I don't know that function is integrable at first. So this is proving that function will be integrable because it's just nu of e. Well, it might not be integral, by the way. I mean, this measure is allowed to be infinite if this function is not in L1. This is a non-negative function, right? G over 1 minus g, if g is between 0 and 1. It's a non-negative function, but its integral could very well be infinite.
It could be infinite at points where g is 0 or 1, sorry.
Even if g isn't equal to 1, it could be going to 1 so rapidly, right? I mean, this could blow up, not because g is equal to 1, but because it goes to 1. So nu is allowed to be, all we know about f is in L1 plus minus, but you know, plus minus of mu, if you're positive, then this is vacuous. You're already in L1 minus. So this is just measurable. I'm saying nothing about the integrability of this function. It's just measurable.
Wait, and what was the statement of the theorem again? What was it that we wanted to prove?
Let's look back. So this is what we wanted to prove, but I want to show you why. Why this is what we wanted to prove. Let's go all the way back. Here's the Radon-Nikodym theorem. Okay, we start with the measurable space. Nu is a sigma finite sign measure. Mu is non-negative, sigma finite. Then there exists unique. They're unique because G is unique. We'll prove the uniqueness in a second, actually. That's an easy argument. Nu A, nu S, which decomposes like this. Nu S is absolutely continuous with respect to mu. It's singular with respect to mu. Nu A is absolutely continuous. Then there's a unique function, which is the Radon-Nikodym derivative, so that for any measurable set E, we have this.
And the uniqueness of F follows from...
We have to prove that. We have to prove that. But what I wanted to say is, what's this condition? This condition is that either F plus is in L1 or F minus is in L1. In our case, F minus is automatically in L1 because F is non-negative. So there is no minus part. The minus part is the zero function. So saying F is in L1 plus minus when the minus part is known to be in L1, because it's the zero function, is vacuous. It's just saying it's measurable. So that's why I can't just stick in 1 over 1 minus G, because what right do I have to integrate that? On the other side, I do have a right to integrate because it's a limit of bounded functional, so I can apply dominated convergence. What I get on the other side might blow up. Yes?
Can we go back to the very last slide?
The very last slide. I like these pieces of... line. Okay. I was going to say, I like the pieces of paper or slides. What happened here?
Yes, so when you're applying the dominated convergence theorem,
Yes.
you're applying it to the left-hand side, right?
I'm applying it to the left-hand side, yes.
So, but it seems like you also took the limit of the inside on the right-hand side.
Yeah. What dominated convergence will tell me is that I can pull the limit from here to here.
Yes, on that one.
Now, once I pull the limit inside,
Yes.
these two things were equal. For any fixed n, they were equal.
Oh, okay.
So I'm just keeping the limit inside. And the limit inside, pointwise, converges to this.
Okay.
So this is keeping the limit inside. Here I'm applying dominated convergence to pull the limit outside.
Oh, okay. So instead of going from the outside in, you kept it from the in. You took it from the inside.
I'm just keeping it inside here. And the limit of this on the inside is this.
Okay.
Okay?
I think it's the same that we also use the dominated
It's this...
theorem on the right side.
Well, I do. So this function doesn't have to be integrable.
Maybe umbrella.
That's
Monotone Convergence.
Here,
It's the limit of sorry.
right? I don't know that this is integrable.
Yeah, that's it.
It could be, this could integrate to infinity.
But then if you keep like the limit on the inside and the right-hand side, then how do you know that the two integrals are equal in the limit? Maybe I'm just missing something.
So that's what, I'm pulling the limit symbol from the inside the integral to the outside.
Right, then you can equate the two.
Then I can equate
So
the
the
two.
question is, when the limits are inside,
Yes,
why are the two sides equal?
Yes.
because they're equal for every value of n.
But without a limit on the inside, like for a
But then
fixed
you're
n.
taking an integral.
But then you're moving the limit on the inside to say they're equal?
Like,
Because it's dominated by.
So like, why can't we just take the limit on the inside?
we consider the two
On the right-hand
functions
side?
and
On the
we
left-hand side,
integrate
why can't
them,
we just
and
do it
then
on
we
the
pull
inside?
the
But we
limit
can't.
outside
We can
and
do
the
that.
left
Yeah.
side.
So
So
the
the
right-hand
the
side.
right
Yeah,
side
that's
is
true.
just
But
the
the right-hand
integration of
CCT even
the
outside.
limiting
But
function.
then the right hand side and limit on the inside is also the same value.
the point is, I don't have a way of, so what am I supposed to use here?
I'm not too sure why we need DCT.
Okay, wait, so there is something I can use here. I can just use monotone convergence on this side, because it's non-negative and I'm just adding up more and more things. So it might blow up, but at least it's monotone. If you like, fine. Dominated convergence on this side, if that'll make you happy. Dominated convergence on this side, monotone convergence. Here, monotone convergence.
The insides aren't equal.
Here, dominated convergence there.
Monotone requires a positive measure?
This is a positive measure.
Yeah, but I'm just asking, monotone requires a positive measure?
We certainly proved it only for positive measures because we proved it for non-negative functions integrated against positive measures, and as long as it's only increasing. Yeah. Okay.
What was the resolution with monotone? I'm sorry.
Well, this thing, because G is between 0 and 1,
Yes.
when you add more and more terms, you're only increasing that size.
Sure.
So that's monotone convergence.
Yes. Okay.
And it converges
I think it does. Okay.
to this. I mean, it converges to this when you interpret 1 minus G to mean the infinite series.
Oh yeah, that's true. Okay. Yeah.
So interpreted 1 over 1 minus G as when I write this symbol, if G is equal to 1, what I mean is, well, that is what happens when you sum that out. But
Yeah.
so with a little bit of care for this being the limit.
Was it E intersect A or?
Here, no.
And the left-hand side is always finite in our current assumptions. So
what I mean is
That's right.
what I mean
That's
is-
right. In our current assumptions, this is finite. That's right.
But like the symbol G over 1, I mean, well, yeah, it would just be infinite. Like
It could be infinite.
Yeah.
I could be integrating an infinite amount, which could happen if, well, it can't happen in this case because we've decomposed nu, which is itself just a finite measure, into nu a plus nu s. But in general, so let's move to the general case where you can see where these things can become slightly more complicated. So what do you do in general? Okay, we can do this in 1 minute. What do you do in general? So if only sigma finite, I'll get to the uniqueness also in a second. If only sigma finite, you can write X as the union of EJ, where the EJs are finite, let's say for both the nu and the mu simultaneously. In which case you can write it as a disjoint union of SJs in the usual way. You take the first one, you chop off anything that's related. On each of the SJs, the nu and the mu are finite. So on SJ, we get that nu is so let's call it nu j is equal to nu j a plus nu j s, and nu j a of e is equal to the integral of fj d mu j, and then you just add them all. Then nu a is a sum of nu ja, nu s is a sum nu js, and f is a sum of the fj's, which all have disjoint supports.
How do we know that these sums of measures are well defined? Like, is it infinite?
They could be infinite.
Yeah, they could just be.
So this was if this is still for nu non-negative, not signed but positive, and if nu is signed, just do it for the plus part and then do it for the minus part and subtract. Sorry. It's true for the plus part separately, it's true for the minus part. That all comes out. While unique, if nu is equal to nu a plus nu s, and it's also equal to nu a prime plus nu s prime, then nu a minus nu a prime, well, these are both absolutely continuous with respect to mu. And it's equal to nu, what, s prime minus nu s? And that's orthogonal to mu. And the only measure that's both absolutely continuous and singular with respect to mu is the zero measure. Questions?
Can you explain again why above the how was it, right, when we do like all the singular stuff and whatnot, right, we need like the disjoint union. How is this getting affected by taking these unions?
So I just know that there's a union, but I can make that union a disjoint union.
Yeah.
And on each of the SJs, everything is finite. So mu j is the restriction of nu to Sj. And mu j is the restriction of mu to Sj. Run the previous argument, that gives you this decomposition into the absolute continuous and singular part. The absolute continuous part is the integral of some Radon-Nikodym derivative.
And there
Of
it's
E, of course.
This decomposition is over specifically like the Sj.
Yes, I've made a choice of SJs.
Hence, when you put them all together, like it's still gonna like,
Yep.
you're still gonna have disjoint
Yep.
pieces.
The support of each of these is Sj. And then, so just put them all together.
Okay.
In this new A equals some thing?
Yes.
Are those gammas?
Those are news.
Those are news?
Those are
Okay.
very quickly written news.
Just check. All right.
So you get the absolutely continuous bit by adding up all the absolute continuous parts, the singular part by adding the singular parts, the derivative by adding the
At
derivatives.
some point you prove, is the sum of absolutely continuous things absolutely continuous? Okay.
Each one of them has measure 0
Yep.
when mu does.
Yep.
So you're summing 0 a whole bunch of times.
For the singular ones, what do you do to get your...
What do you do?
Pick unions or something?
Yeah, if mu is not 0, well, each one of these has to be 0.
On the D thing.
Yeah. Take a set on which mu isn't 0.
And then take the unions of the A's, AI's, or whatever.
Yeah.
they're. Okay.
So you've decomposed the SJs into AJs and BJs.
Yes.
So A is the union of the AJs and B is the union of the
Yeah.
BJs.
Hmm.
So the point is this compartmentalizes. You can parallelize the process. Do it on the pieces, add them together. If it was signed, again, just break it up by the Jordan decomposition theorem and do it on the pieces. And when you get down to it, you'll get some decomposition, but that's the only one you could have ever had.
And when it's complex, what happens?
So we didn't talk about complex sign measures, specifically because now you have to decompose it in some kind of integral way. In fact, I was going to move on and not talk about the complexities of complex measures. But if you want to, we can. I was going to move next to finish the story of absolute continuity and antiderivatives, the other fundamental theorem of calculus, and Jordan measure, Jordan content.
That stuff is in the qual, right?
Absolutely is.
Jordan content?
The
No.
absolute
The absolute continuity and
Oh,
the
and
yeah, the fundamental theorem.
Yeah.
Yeah. So okay. So that I have to get through. That's where I think we'll start on Friday.
So what are uniqueness of G over 1 minus G?
Uniqueness of.
G over 1 minus G?
Oh, the function limiting. Yeah.
So forget how we got it. Any decomposition like this into an absolute continuous and a singular is unique.
That still means that you could write nu A as some other integral, right? You have the unique nu A.
The uniqueness of G of thank you.
Yeah.
Thank you. So what that says is the integral of E of some function d mu is the integral of E of some other function d mu.
Yeah.
And these, so in the case, let's do it on the plus part and the minus part separately. Because if you have a plus part, then it decomposes f into f plus and f minus. So then take the difference. That's 0 on every set, in particular 0 on x. So it's 0 almost
zero
everywhere.
almost everywhere.
So they agree almost everywhere.
Yeah. So they are in the same equivalence class.
And positivity.